In-class activity 17C. In 2016, United States consumers spent approximately $811.125 million on food, while Pakistani consumers spent about $92.638 million on food, and Swiss consumers spent about $31.930 million on food. Part A, is this enough information to decide in which of these countries individual consumers spend the most on food annually? No, since the countries are not the same size, the total spent is not a good measure of how much individuals spend on food. Part B, suppose you also knew that in 2016, there were 322.9 million people in the US, 203.6 million in Pakistan, and 8.4 million in Switzerland. Could you now rank the annual amount spent on food in these three countries from lowest to highest? Well, now we can. Now we can calculate the annual average cost of food per person. In the US, we'll do the US first. Let's see. Whoops, let's start writing with the pen. In the US, we're just going to take 811.125 and put that over 322.9. And this is going to give us in dollars 2512. And then we'll do Pakistan next. It's 92638 over 203.6. And in dollars, that'll be 455. And then Switzerland, 31,930 over 8.4. And this is going to be 3801. Just calculating the averages. So we can see that Pakistan is going to be the lowest, Switzerland the highest, and the US is in the middle. Objectives for the activity. You will understand the graphs of rational functions may have slant asymptotes. You will be able to use the equation of a rational function to determine whether the graph of the function has a horizontal asymptote, a slant asymptote, or neither. If a rational function's graph has a slant asymptote, find the slope of this asymptote. Moving up to the next page, number 2. Food expenditures in the US between 1988 and 2013 can be modeled by the function E of t, where E is measured in millions of dollars and t the number of years after 1988. During the same time, the population in millions of the US grew following the model P of t. Part A, write a function f which models the amount spent per person per year on food t years after 1988. So let's write f of t, and we're going to put the function e in the numerator. So we get 44.419 t squared plus 7855.5 t plus 480926. That's the numerator. The denominator is going to be the function p, so we get 3.0245 t plus 240.02. Part B, use your function to predict how much Americans will spend on food per person in 2025. Okay, so in 2025, it's going to be, we'll have to figure out t, so it's going to be 2025, and then it's minus 1988, which is going to be 37. So we're going to take f of 37, and everywhere in the f function that we wrote above that we see a t, we're going to replace that with 37. Okay, moving to the denominator, 3.0245, 37 plus 240.02. Part C, how fast is the cost of food per person rising between t is equal to 20 and t equal to 25? So what we could do, let's do this. We're going to write f of 25 minus f of 20 as the numerator, and then we'll have 25 minus 20 in the denominator. So if we figure all this out and do all the numbers, number crunching, we'll get 2233.85 minus 2182.30, and then Denominator easy, that's just 5. And when we figure this out, the answer is going to be in dollars, and it's going to be $10.31 per year. Number 3. Now let's study the long-term behavior of the function f from question 2. Note, mathematical models such as this one are generally not accurate far into the future. In this problem, we are studying the behavior of the mathematical function f, even though it's not likely to be a good model for food costs many years from now. Part A, does the graph of f appear to have a horizontal asymptote? No, it doesn't. Part B, how fast is the function increasing between t is equal to 490 and t equal to 500? Between t is equal to 990 and t when t is 1,000. Okay, so let's do this in 2 parts. The average rate of change. So this is just part B. So we'll do the average rate of change between t is equal to 490, that's an equal sign, and 500. Okay. We're going to do the same thing that we did in the last question. F of 500 minus f of 490 over 500 minus 490. This is going to give us 1455 per year. And that's in dollars. Now, the average rate of change when t is equal to 1,000 and t is equal to 990. Squeeze it right here. F of 1,000, oops, there we go, minus f of 990 over 1,000 minus 990 equals 1465, and that's dollars per year. Part C, let's scroll up, there we go. Calculate, oops, yep, it says calculate the ratio of the leading terms in the numerator and denominator of f. How might this ratio help you predict the rate at which the function is increasing for large values of t? So the leading terms, let me go back and look at these two functions here. Where did it go? There it is. Okay, so let's go back to part C. So we want the leading terms. So the ratio of leading terms is going to be 4.419 t squared over 3.0245 t. Okay, so it looks like if we reduce this and we divide this, we'll get a number that's approximately 14.69 t. And it looks like the average rates of change we found in part B are getting closer and closer to the coefficient 1469 per year. And that's just from part B right here. We got 1455 right up here. And then we got 1465 right there. And it looks like we're heading to 1469 per year. Part 4, let me just move that up. This is the graph of the function. F of x equals 4x squared minus 2x plus 1 all over 2x is given by the solid curve in the graph below. The dashed line is its slant asymptote. A slant asymptote is a line which matches up with the long-term behavior of a function. Okay. Part A, what characteristic of the formula f of x suggests that the graph has a slant asymptote? Well, we would look at the degree of the numerator and the degree of the denominator. And when, I'll write this down, the degree of the numerator is exactly 1 degree greater than the degree of the denominator, and there's going to be a slant asymptote. So the degree of the numerator is exactly 1 degree greater than the degree of the denominator. Part B, use the graph to find the slope of the slant asymptote. So the slant asymptote is going to be, or the slope of the slant asymptote will be 2. Part C, how can you decide the slope of the slant asymptote directly from the formula that we have for f? Well, taking the ratio of the leading terms gives you 4x squared over 2x. Let's see, that x can go with one of those. 4 over 2 gives us 2, and we're left with 2x. And the coefficient, so the coefficient is the 2 there, of x in the ratio is the slope of the slant asymptote. Part 5, for each function, decide whether its graph will have a horizontal or a slant asymptote, or possibly neither. Find the equation of any horizontal asymptote, find the slope of any slant asymptote. So for part A, we're looking at the function f, and it says, the degree of the numerator is 3, the degree of the denominator, or the leading term, is 2. So the degree of the numerator is exactly 1 greater than the denominator's degree. So the graph will have a slant asymptote. There we go, slant asymptote. And if we compare the leading terms, we get, that's a 3x squared over 2, or 3x cubed, excuse me, over 2x squared. Those two are going to go with one of those, and we're going to have 3 has x, and I guess the slope is going to be the coefficient of 3 halves. Part B, oh, neither. Okay, part C, that it's going to have if we compare the degrees of the numerator and the denominator, the graph is going to have a horizontal asymptote, and the equation of the horizontal asymptote will be y is equal to 0. That's the end of this video.